It's great to be here with ODSC. You guys have fantastic events, and we're just delighted to be able to share a little bit about Edge AI. Yeah, for starters, I'm Seth Clark, so head of product over here at Modsy. I lead up our design and engineering and data science activities, essentially creating the platform and the product that we've brought to market. My background's actually in ocean engineering, so I may be the first former yacht designer that has had the opportunity to present here. But I studied computational fluid dynamics at MIT, went to grad school, got a degree in high performance yacht design, and then about a day before my graduation, Bear Stearns collapsed, as did Lehman Brothers. So it ended up being an interesting time for folks in the boat world, and I discovered there was this burgeoning world of data science right around the late aughts, 2008, 2009, and doing math with computers for fluid simulations turns out to have a lot of overlaps with the world of data science. So I've been doing AI, data science, and analytics product development for a bit over a decade at this point. Worked as a director of data science for a while in the consulting field before founding Modsy. And one fun project from very long ago that still kind of connects me back to this day. A team of mine back when I was an undergrad, we were building an autonomous kayak to float around and drive around the Charles River up in Boston. And I think a lot of the pain that I had trying to get that stupid robot to work has stuck with me till this day. And so hopefully that will be pain that we can save you all from as you're getting into this world.
That's a tough anecdote to top, admittedly, but great to meet up, everybody. My name is Brad Monday. I'm the head of our machine learning engineering team here at Modsy. As Seth mentioned, really excited to be here. Looking forward to today's discussion. By way of a quick background on myself, I studied applied mathematics in school, attended Johns Hopkins in Baltimore, and kick-started my career in the tech consulting world, where I had the opportunity to work on a lot of really awesome data science and analytics projects for both government and commercial clients. During my time, I built a lot of complex AI ML models, but also had the opportunity to apply those to a variety of use cases and a variety of deployment environments. So worked in Databricks and Spark clusters, on-prem, in some cases disconnected environments and completely air-gapped networks, in addition to kind of the more traditional cloud and edge paradigm. So today that's helped me because I work with our customers a lot and help them integrate Modsy into their own tech stack. And when we think about Edge AI, it's evolving every day. And for us, no 2 days are the same. It's awesome to be able to help our customers design super complex production systems where they have dozens and hundreds of models running across a whole collection, broad array of infrastructure, edge devices, on-prem, cloud, etc. So that's a quick background on me. As I'm talking, I'm realizing, Seth, our audience may benefit from learning a little bit what's behind you. What Seth didn't mention is he is a jack of all trades, an engineer at heart, and he applies that to his personal life as well. So Seth, would love to hear about what's behind you on that wall.
Yeah. You guys are joining me here in my home lab that I've been working out of since the pandemic, when my wife kicked me out of the formal office. So I have now adapted our downstairs worker lab, makerspace, into my professional daily office. So what Brad's probably referring to is back here, I have this little wall of edge devices. And this is where we actually do a lot of R&D and prototyping within Modsy, testing out some of the software that we're developing, testing out different use cases, new hardware devices. One of the things that I think is most exciting about this Edge AI world is that for 40 bucks, if you can find one, you can buy a Raspberry Pi and you have the equivalent computing power that 5 of the laptops I used in undergrad had at the time. You get multi-cores, 16 gigs of RAM, high performance, storage, and you can do this with a couple of watts of power. One of the things that I think is so exciting about that is not only do we have this insane density of computing power in a really small device, but they can go anywhere. You can take this into places that computers have never been able to go before. So one of the things that inspires me and gets me really excited, and one of the reasons why Brad and I are talking to you here today, is because we are so optimistic about what's possible when we start to rethink where should computing happen. There's so many great use cases for computing in cloud environments. There's a lot of great stuff that comes out of the scale and efficiency you get from AWS and Azure. But as we'll talk about today, there's some really cool things that you can do with a Raspberry Pi, with a Jetson Nano, with a physical server out in some rack in the field somewhere where you don't have any internet that you can do, and that with the application of new machine learning techniques to get models really small, have unlocked a level of computing in new locations that we could have never had access to before until today. So I think it's an exciting field. I think it's still rapidly evolving and changing. And I expect a lot more advancements in the coming years, both in terms of computing power, access to more exotic GPUs, as well as the ability to start using these models for more interesting things. So that leads us to, what are we here to talk about today? What is this edge AI concept all about? And why do we care about running machine learning models at the edge? Well, there's really two giant paradigm shifts that have happened over the course of, about the past decade or so. One is that computer chips are just everywhere at this point. You can get access to a huge range of chipsets, formats, form factors, different architectures. The adoption and the growth of ARMs chipsets have provided access to like really high power, but high speed, but low power computing capabilities. And at the same time, edge data is growing incredibly fast. I think in 2020, somewhere around 15% of all enterprise data was being generated at the edge. But by 2030, it could be up to 75% of all enterprise data coming from big companies are going to be generated at edge locations. So when you combine the fact that you've got chips in everything, from refrigerators to cars to Raspberry Pis to drones, with the fact that so much more data is being captured at the edge, your Ring doorbell camera, the sensor inside your fridge telling you that the apples are about to expire, all of this data getting generated there, it's leading us to a path of saying, when you want to take advantage of this data, mine this data to make interesting applications, to solve problems, you actually want to move that computing to where the data is located. That's really the big transformation. That's what we're here to talk about today, this idea of moving compute so that it's not just centrally located in one big hub, but that you can move your algorithms, your models, your machine learning tools to where the data is located for a number of benefits. Can you jump to the next slide, please, Brad? So when we talk about edge, we are very inclusive with this definition. I think of edge as sort of anywhere that you want to run a machine learning model that's maybe not in one location. So any use case where you have a model and it needs to run on two different computers, you're working in kind of an edge paradigm, because you need to think about location. You have to have a location-centric mindset when it comes to running these machine learning models in all these locations. So you can have edge applications that include compute in the cloud. It can include compute on-premise, hybrid environments where you have some stuff on-prem, some stuff in a private cloud, some stuff in public AWS or Azure. These are all edge applications, in addition to the traditional things we think of with edge, like the Jetson Nano, the Raspberry Pi, the Intel Upboard, the traditional kind of small form factor edge. When you think about all these locations and environments, it's pretty easy to tell that there's a vast amount of variety in all these locations. So how do you handle that? Well, there's kind of two main factors that differentiate edge devices as we see it. One is its power consumption. Edge devices have a ginormous variation in their power needs, how power hungry these devices are, as well as a big variation in network connectivity. So one of the two factors that we found to be most helpful in tackling this challenge, figuring out how to run models in all these locations, is to segment your devices based on their power consumption, as well as how much consistent network access you have available. So on one extreme, what you might call the near edge, you could think of something like a 5G tower. So we've got cell towers all around us. On those cell towers, literally at the base of these towers, there are racks of servers, and they're doing a whole bunch of different things. A lot of it has to do with just data transmission, of course, but those servers are getting access to even more high-powered computing resources, things like GPUs, so that you can have scenarios where if you want to have a machine learning model running really close to someone's cell phone. I don't even know where I put my phone. But the model is, let's say it's too big, too complicated to run right on the phone. You can kind of have this hybrid solution where you can run a traffic rerouting algorithm that's a giant, really sophisticated and complex neural network. And instead of running it on the phone, you can run it right at the cell tower on a big rack of GPUs that it has available to it. The reason why you might want to do that is when you're driving in your car, you want to recalculate your new path as quickly as possible. And the latency of going all the way back to the cloud for that inference and returning it can be on the order of a few hundred milliseconds. And depending on the situation, that can be too much. So the near edge includes scenarios where you just want to get your computing resources as close to that end application as you can for speed. Manufacturing facilities are a good example of that. Kind of the other end of the spectrum, you have scenarios where you have either low power or inconsistent network access. So this could be microcontrollers embedded in, again, different smart IoT devices. This could be servers that you have that are just offline. There are computing resources on ships. There are computing resources on offshore oil rigs. There are computing resources in data centers in parts of the Midwest that don't have as high speed of internet as some of the coasts have. In all these situations, it can be really useful to be able to move your computing, move your machine learning stuff to those locations, so you're not waiting for that data, if it ever comes, to transfer all the way back across from the edge device back to the cloud. So when you're thinking about edge, when you're thinking about edge architectures, you're going to want to focus on flexibility, a solution that allows you to address all of these different power requirements or locations, and efficiency, so that you can take advantage of high-powered stuff in the cloud and then low-powered stuff out on the far edge. All right. So Brad, can you tell us a little bit, you've worked with some of these devices before, what it's like to just get one device kind of set up to run some machine learning models? What does that look like?
Yeah, absolutely. The first thing I'll say, I'll just start by saying both Seth and I have done this manually several times. It can be very time intensive. It can be tricky, and there are a lot of places where you can go wrong, where a small mistake may lead to some sort of catastrophic event with your small form device. Again, configuring this small edge device to be able to run a machine learning model. So, why is that? Well, I think that there are several layers of complexity when you think about setting up a device, in this format. So, starting with the device itself, oftentimes you'll have to install the operating system, and the operating system you use will differ based on the device. There are also system level dependencies that you need to install that your model will ultimately need to run. We'll talk about that in a second. And then another thing,
actually, as an example of that, this is probably 5 years ago. I had a project at work where we were developing a demo for one of our clients to run on a Jetson TX2 board. So that was one of NVIDIA's kind of earlier form factors of their edge-oriented graphics processing units. So it was this, I don't know, it's probably about that yay big, giant development board. And it took me 5 hours to just get the operating system installed and try to run one model on it. And what it came down to was basically there was just like a crazy amount of dependency mismatches. The operating system that came pre-installed did not support the library version that particular model was trained to use. And so after a lot of restarts, reinstalls, changes to the operating system, reviews of the dependencies, going back and pulling previous versions from GitHub, and then compiling them manually to deploy on the device, we finally got the thing working. But running someone else's code shouldn't take 5 hours to get started. It was a terrible experience. I left with some scar tissue that day. So I just wanted to share that in case you all have felt that pain before.
Yeah, right. And amongst that, what Seth just kind of shared as an anecdote, there's a lot of other things you need to consider. So another one, importantly, is resource constraints. How much RAM, disk storage, number of CPU cores are available on that device. And when you think about an Edge AI app, your model will be one process that's running, but are there going to be other processes running simultaneously that you need to allocate and kind of share the available resources across? Another layer is any external software required by your app, things for custom data connections, any other monitoring or logging tools that may be required by your service. Seth, I think I remember we were trying to set up the exact same application on both your Raspberry Pi and Jetson Nano, and had some difficulties doing so, right? Can you share a little bit about that experience we had?
Yeah, so the Raspberry Pi and the Nano, just again, is simple examples of like the diversity of edge devices. They have the same header pin configuration. So there's a set of pins here and here that have the same combination of values. They're arranged in the same way. So it sort of feels like you should be able to just plug and play in the same way we plug stuff into our USB ports on laptops, and everything just kind of works. Well, it turns out that the interfaces for those header pins, even though the pins themselves are basically there to do the same job, they have vastly different implementations between the Jetson and the Raspberry Pi, and it has to do with really specific board-specific chipset stuff. So every time we were trying to basically take this other example we built out and run on a Raspberry Pi, move it over to the Jetson Nano to try and take advantage of the fact that it has a built-in GPU that makes models typically run a lot faster, it was a giant cluster because the libraries that we were using were, again, not compliant. And so it took a lot of hunting and Googling and searching on Stack Overflow to see if we could find a comparable library that would work on the Jetson. So just it goes to show that that process can be really painful.
And every device is different, and the dependencies and dependency management becomes very difficult. Two other layers that you need to consider. One is security. So, who is going to access and how often are they going to access this app? Do other systems need to access it? What are any networking constraints? Is it going to be, as Seth mentioned earlier, in a fully connected network, or will it have to operate in a completely disconnected offline setting? And then finally, the model itself, which we haven't even talked about. Number one, how are you going to download the model onto the device? Number two, what programming languages might you need on the device to actually run that model? And what about any frameworks? As an example, let's say you're building a computer vision model, and your model may use OpenCV to do some of the image processing. Well, OpenCV requires a whole list of underlying system level dependencies, and as you can see, we're back at square one, and things can become get mixed up. So the point is, Seth could spend 5 hours configuring one device, and for small use cases, 1 to 2 models, a handful of devices, that's manageable. But when you think about a production edge AI system, and you're dealing with hundreds of models on thousands of devices, this manual approach simply is not scalable. So what I'd like to do next is discuss some ways that we can solve these challenges, keeping in mind all those considerations we talked about and consequences of some of the decisions that you make. So let's put on our engineering hats for a second and build, an ideal edge architecture, and we'll go through a little bit of a design journey. So, if we're defining from an engineering standpoint what an edge-centric architecture might look like, the first component would be a central management hub. So imagine if instead of having to manually configure a device to run a machine learning model, you can instead define a configuration with the model itself, any model-specific dependencies, and underlying system level dependencies that you need to run that model on a device. Imagine if you can define that configuration once and send that out to your entire fleet of devices. It makes things a lot easier. So once we have that in place, another pillar that's really important is that we want this architecture to work on any device. So when you start to work with some of these small form edge devices Seth mentioned, IoT devices, they come built with an ARM chip. And so we want to make sure that our architecture is agnostic of chip, ARM or AMD, and that there are any specific data transfer protocols that we account for. For example, in manufacturing IoT, the industry standard is they use MQTT. We want to make sure that the architecture we build can work with MQTT, gRPC, REST, etc. A third requirement is more self-explanatory. We want our architecture to yield low latency inferences, and performance matters all the time, regardless of where you're running machine learning, but especially in some edge cases. You can think of navigation use cases, AI use cases, and smart cars. Security or perimeter security all requires that rapid inferencing. And then finally, we want a requirement to be that this architecture we build can operate in a completely disconnected environment. So we talked about that a little bit. Seth, in your experience, have you ever worked on a project that required a completely disconnected model? In other words, deploy a model to a device once, and it needs to operate uninterrupted, kind of very smoothly in a completely network restricted environment?
Yeah, I mean, one of the spaces that has the least network connectivity possible is underwater. I don't know if you guys have ever tried syncing a Bluetooth device while you're 20 feet down. It's not going to happen. And it's because water is not very friendly to radio waves. They're just way too high frequency, and the water molecules just do a number on them. In fact, it's actually kind of interesting how ships talk to underwater autonomous vehicles, AUVs. They have acoustic modems where they're basically using sound data to package up information, and they're able to send the sound data because the sound travels through water much better than radio waves. But that is super slow. If any of you are privileged enough to not have to have dealt with dial-up, you're lucky, because those of us who lived through the dial-up phase know how long it took to load a single web page. That's basically the technology you're stuck with underwater. So if you want to use machine learning, one of the projects we're working on today is to help one of our customers basically deploy target recognition models onto AUVs so they can just operate completely independently. So not only is it slow, but in a lot of cases, there's just no way to connect. These devices are designed to go hundreds of meters underwater, go do some stuff, sometimes reconnaissance, sometimes ocean surveys, and then they have to come back up to the surface to get a satellite link to be able to transmit what they found. So you need a solution where you can just run that model and know it's going to be bulletproof and keep doing its job no matter what happens.
Yeah, that's a great example. Thanks. So why don't we talk about the recipe for actually building this type of architecture?
Yeah, so you take all those kind of design patterns into account that we just talked about. We have a perspective that there's a way to approach this that's edge-centric. So rather than thinking about things in terms of there's the cloud and we're sending things out, trying to think about the edge devices first, and then creating a system where we can then correspond, interact with, kind of configure those devices, but we're really thinking about the edge device from first principles. So if you tackle this edge-centric AI approach, it can really help manage the chaos that comes with dealing with all these random devices. So the key ingredients will include a few items. One, containers. We found containers to be one of the best ways to make sure that when you create a machine learning model, it's got all the stuff, all the random libraries and tidbits and scripts and data files and assets you need, all in that container in an immutable format. Basically means that if that container works, it's going to always keep working because the dependencies are all locked inside. That provides a lot of flexibility to be able to take your models and run them on a range of different devices. One of the other pieces is a central model store. So you need a way to host that container and then allow edge devices, when they're able to reach out and grab those container images, basically get a hold of those models. Again, from an outside in standpoint, edge-centric. You're gonna need multiple devices, one or more devices. What's interesting though is this isn't just small single board computers. This can include cloud and on-premise resources. And this is a really great way of getting around the challenges associated with multi-cloud compute. When you have workloads or scenarios where you've got some stuff in Google, some stuff in Amazon, some stuff in Azure, for big companies, this is not uncommon. You can use edge-centric to basically remotely process your data in all these locations using the same models. You need some kind of container runtime. We're big fans of Docker, so we'll be talking about Docker today, but it could be Containerd. There's other runtimes out there. And then some kind of API, REST or gRPC for high speed, low latency, kind of rapid response. gRPC is fantastic, but it's a little bit less user-friendly to work with and look at. So for scenarios where maybe you're just working offline because of network speed, but latency is not super important, a REST interface is fantastic. But with these 5 ingredients, you can create a pretty robust edge-centric solution that has a number of benefits. The first benefit is really that it provides incredible low latency, high speed performance, because you're moving your compute right to the data. You're putting the computing resources right next to the data. And whether that is a Spark cluster in another region, another continent away, or whether it's this little camera attached here to my wall, which we're going to take a look at in a second, we're doing the inferences, and it has to travel about 11 inches from the camera right to the sensor that's doing the processing. That's awesome. Secondly, it's really efficient with resources. You can take advantage of machine learning with a lot of modern tools today and get those models quite small, quite efficient, quite limited in size, and then distribute those models to run on lots of smaller devices. That can actually be not only efficient with the hardware that you have, but it can be cost efficient. Rather than taking advantage of really huge, expensive clusters, you can minify your models and take this edge-centric approach to distribute it and run it on a bunch of small computers. This could be people's workstations, laptops, small edge devices. You have a lot more flexibility with how you decide you want to use your compute budget. It's resilient on slow networks, as we talked about. And it's not just for single board computers. You really get to take advantage of the fact that all of these models can run on any other computer you decide to connect up to your fabric of edge devices.
Yeah, so any interest in seeing a demo?
I think that'd be awesome, Brad. Yeah, can you show us what this looks like after
Cool.
Talking everyone to death for half an hour? Let's see some cool stuff.
Yeah, we'll mix it up a bit here. And what we'll do now is walk through the first of 3 demos that we're going to show today. Again, what we want to show is just a couple of real life examples of how you might implement this edge-centric architecture that we've introduced thus far. So the first demo that we'll go into today is a very simple NLP web app. What we do, we have a TinyBERT text classification model, and we pulled it down from Hugging Face. And we containerized that model, we deployed it to our central model ops platform, or MODSI, and then we've remotely deployed that to this device. So in this case, we'll deploy it directly to Seth's Raspberry Pi 3B model in Fairfax, Virginia. And then we built a very simple web app that allows users to put in some text. And what we'll do, I'm going to be running that from my laptop. I live in Philly, and that will send the data to the model running on the Pi in Seth's office, 5 feet behind him. It will take the predictions and return them back to the user. So high level, this is the demo design. Let's dive right in, where I'll provide some more details. Let's see here. Okay, so can you give me a thumbs up? You can see the browser.
Looks good.
Okay.
Could you give us a little Command plus action to increase the font size just a touch? I think it'll be easier for us to see.
Does that make it any better?
Yeah, that's definitely better.
Great.
Thanks, Brad.
Okay, so again, we found this TinyBERT model on Hugging Face. You could find hundreds of state-of-the-art great models here, directly in this library. And what we're going to do is we're going to take that model and convert it into a container. And how are we going to do that? Well, we've built an open source project, I alluded to this earlier, called Chassis ML. What Chassis will do is, without having to know anything about Docker, APIs, web servers, etc., it will convert any Python model into a production container. So how does this work? Again, it's open source, as I mentioned. All you have to do is install the Python package Chassis ML, and you can start using this today. The general idea is that you can load any model into memory in your Jupyter notebook or other Python editor and define a simple function. Think about this as your inference function. And in this function, we'll take in some data, and the example we'll show it will be text data. We'll send that process data through your model for predictions and take the outputs, structure them however you'd like. And all of this code will be executed inside of a container that will be automatically built by Chassis. And then Chassis does the rest. And essentially, we'll take your model and all the dependencies required to run that model. It will serialize it, it will build a container out of it, and it will push it to some Docker registry somewhere. It takes a couple minutes, and suddenly you have a production-ready container that I could pull down and run on my laptop, run in Kserve and Kubernetes and MODSI, and really anywhere that you need to run that model. It's truly interoperable. I'll just point out one thing on the Getting Started page. Feel free to check this out. There's very detailed annotations in this Getting Started guide. But what you'll also notice is you can build models specific for different target architectures. So by default, it will build for AMD chips, but if you set this ARM64 flag equal to true, it will build it for an ARM chipset. So this is step one. We'll take this Hugging Face model, use Chassis to build a container out of it, and then we'll deploy it to MODSI. And so I'll show you an AMD version. We ultimately built a ARM version as well, but now it's in my central library. And what that means is I can access this with a simple to use API. So with a couple lines of copy pastable code, it's a standard API that allows me to access any model in my library. And what we can expect is some output by the model to return 6 classes with a corresponding confidence score of the text that we input, joy, sadness, anger, etc. taking this a step further, we talked about how we can then deploy this out to a particular device. And the way that you do that is through our device group feature in Modsy. So super simple. All you do is select the model that you'd like to deploy. So we're going to deploy our TinyBERT algorithm here. And what happens is you can see the device it's deployed to, and we get immediate telemetry data back from the device itself. So we see some of the resources, we talked about that earlier, fairly limited. And we see it's at Seth's house, right outside of DC. And we also see this standard API contract. It's the exact same set of APIs. The difference is the URL by which you can access this is, the IP address specific to Seth's house. So it makes it super easy to build apps on top of, again, as a simple, fun proof of concept for this first demo. So why don't we jump right into it? And I'll make this a little bit bigger. So here we have a very simple Flask app that I launched from my local desktop. And why don't we put in some text here? ODSC puts on the best events. And right away, we see some outputs, right? You can see how quickly that happened. And again, to reiterate, we sent data from Philadelphia to the Pi running right at Seth's store office in Fairfax and got the results back instantly.
Oh, it's hot. I can tell you're running. I can tell you're running inferences. It's heating up.
I'm sure. What I'll do now actually is pull up a terminal so we can see what's happening behind the scenes here. So let's run another inference. We'll try to change the output a little bit. This rainy weather in Philly is starting to annoy me. We see on the right those gRPC calls right away. I've logged into that particular device. Maybe the model didn't perform too well. That's okay. Anyways, the idea is it's very simple to build apps with those APIs on a model running on Seth's Raspberry Pi. Now, you might be wondering, when would I realistically ever run an NLP model on a Raspberry Pi? Very valid question. And maybe for production, it wouldn't be super relevant, but it's a fun little demo to put together. And what it does is it demonstrates a broader concept and kind of proves this concept that with any model, convert it into a container, you can run that anywhere. And through Modsy's EdgeCentric architecture, you can scale this up to hundreds, thousands of devices, very rapidly.
Also, AWS computing costs are getting pretty expensive. So if you can host your own AI server on a Raspberry Pi at your house, it may be worth the money.
Yep. Couldn't agree more. So let's go back to the slides and talk a little bit more about architectures. We said we would talk about architectures in this webinar, so let's actually talk about some instead of just the benefits and how to build them, right? So if you take this edge first perspective, there are several what we call design patterns that emerge. And these design patterns will be different based on the device or devices you're working with, the specs of those, the use case, and a whole plethora of other custom requirements. So the first design pattern that we'll see is what we call native edge, which is great for static model workloads. In fact, what I just showed you was an example of that, where the compute, the processing is happening on the device itself. So we use Modsy as our central ModelOps platform. We have our model. We remotely push that to the Raspberry Pi. And then it was operating in a way that we could access that via API. And that's all facilitated via and orchestrated via Modsy's EdgeCentric solution. So you can deploy models anywhere. And then on the device, there's a whole plethora of tasks you can do, right? So Modsy Edge can start the container. It can stop the container, restart the container at any time. And then on a case-by-case basis, you can customize resource allocation, on per container basis. So super flexible, and again, very simple demo that we suddenly, can rapidly scale up to hundreds, thousands of devices if we want to.
Yeah, some great examples of that in practice today include, a lot of computer vision scenarios. So any situation where you want to be able to run a model right on a GPU accelerated smart camera, it's a great example of that kind of use case, native edge, as well as sensor data. So if you're processing sensor data live in the field, scenarios like sort of machine failure prediction, or if you're trying to sort of analyze real-time location data for supply chains. We work with a customer who's actually looking at trying to use this information to reduce forklift collisions by basically alerting drivers as they're whipping around corners inside a big factory. So scenarios where you need that data kind of rip through really fast, this native edge approach is really helpful. So computer vision and sensor data, those are two scenarios where you may consider this architecture.
Yeah, yep, that's great. Thanks, Seth. Moving on, the next design pattern we see is similar to what Seth was just describing, something that we call network local, which again is similar to native edge, but can handle larger workloads. So let's do a quick comparison here. We can deploy a single model to that Raspberry Pi, and you saw some of the telemetry data that was returned. And maybe you can get away with a 500 megabyte model that requires a couple hundred megabytes of RAM to run. What we're now proposing is deploying your model or models to an edge server, a more enterprise-grade server, for example, the HP EdgeLine series. It's a bigger box with dedicated resources that can handle these large data workloads. You could deploy dozens of large models, 20, 30, 40, 50 megabytes or gigabytes of RAM on a single server box, and it can process data simultaneously. So let's take, for example, a factory where there are hundreds or thousands of sensors and cameras collecting all different types of data. And in this factory, there may be a handful of AI ML use cases where you want to process all this data at the same time. So what you can do is hook up all your models and your edge server to all those sensors. You can process all that data and run things like different use cases for employee safety, air quality index prediction, or PPE detection. Supply chain management and inventory predictions, quality assurance on the assembly line, to even perimeter security with computer vision. You can run all those workloads simultaneously. And then when you think about scaling this out to hundreds or thousands of factories around the globe, makes it really easy. Again, all being able to configure that from your central model ops platform, as you mentioned.
Yeah, the really nice part about that, especially in the manufacturing or like retail scenario, is that you have a central hub. So for the enterprise, for governance purposes, there is one view of like where all these models are, what model versions are in play, who's using them. But when it comes to operations, that model is literally located on the factory floor or in the retail store. And so you can guarantee that the model is going to keep performing even if AWS has a hiccup, network connectivity goes down. You don't have to worry about the actual execution of it, while you still get the benefits of the governance and visibility into what the heck is happening across all your different locations. So those are two markets where that approach is really helpful.
Yeah, absolutely. Great examples. Moving on, the third of 4 design patterns we'll talk about is something that we call edge cloud. This is great when you may have several sites where the model workload at each site varies significantly. And so instead of just deploying your machine learning models to that edge server, now what we're proposing is deploying your entire model ops platform onto that edge server. So imagine you deploy your entire platform to the factory. This opens the door to several benefits. Number one, the factory has access to your entire library of models instead of just a few. It would be quicker to test different models, to switch them in and out for different applications. You still have the flexibility to send models directly to small sensors in your factory. And data science teams, this might be very advantageous for them, who are assigned to a particular site, and maybe the data for a particular site is so different than any other site that the data they work with, and as a result, the models they build will only really be relevant for this one instance. Then by creating this kind of private edge cloud, your models, your data, and all the infrastructure and sensors located in one area kind of are confined to this private edge design pattern. Seth, any other examples to add to this one?
Yeah, I'll give another one because I have to make all of my examples today about the ocean. Big ships also have server racks on them. And so this is a great example of a scenario where you might want to deploy a whole range of machine learning models to a location that has sufficient computing resources, but again, you can't guarantee it's going to have network connectivity. So that could be an oil rig, it could be a ship, it could be you know, a server rack in the closet of a national park building that's using machine learning models to track various, you know, weather data. So all these scenarios where you're not always certain what access you're going to have to, you know, dedicated cloud resources, this gives you kind of that, the benefits of the cloud, a central hub with all of your models, but locally available. So it's just another way to think about that edge-centric mindset.
Yep, that's great. Thanks, Seth. Just so everybody knows, I am seeing these questions come through. We will address the questions at the end, but for some of these, I'll try to address that in the remaining of the next couple demos that we show, just as an FYI. And finally, the last design pattern is something that we call remote batch, which is great for running large batch jobs in remote Spark clusters. So imagine you're a multinational corporation or a global bank and you collect millions of data points daily. And perhaps that you store all that data in clusters that are co-located by region, right? And so you may have a dozen Spark clusters around the globe. And instead of taking all that data and sending it to where your models are, instead you can take models and send it directly to those Spark clusters and run those large batch jobs. And then again, because of that central, you know, configuration platform or hub, you're able to very quickly send updated models out to those clusters and, you know, receive any telemetry or monitoring data back that you may need to make improvements. So with that, we have a couple more demos to show you guys. And I'll start with this defect detection demo and then hand it over to Seth in a few minutes, not quite yet. For this demo, what we've done is we've simulated a manufacturing use case. And for this manufacturing use case, let's take a manufacturer who wants to automate their QA and QC process. And so they're manufacturing a bunch of parts that go through the assembly line, and they want a computer vision model running on a web camera and being able to detect whether or not there is any defects that happen in the manufacturing process. So what we did behind you, you'll see some 3D little 3D printed gears that Seth created. Again, he's a jack of all trades. He has everything in that office. And he manually made some defects that you'll see in more detail in a little bit. And you know, what we did is we captured a bunch of data, we imported that into Label Studio, we manually labeled it, and then we trained a custom YOLO 5 detection model. With that, we followed the same process I demonstrated earlier. We containerized it with chassis, we deployed it to our central model ops platform. In this case, you know, Modsy is being hosted in the AWS US West region in Northern California. We've taken the model, deployed it to Seth's Jetson Nano that you see behind him. And as you can see that plate spinning, what we'll do is input that video stream in real time and then generate an output stream with the detections rendered, you know, on each image frame. And I'm gonna spin up a simple web application and show you what that looks like again from my laptop here in Philly. So let me switch over to my browser again. And this time, let's go to defect model here. So again, deploy my model into Modsy. We can see some more metadata here, including some performance metrics we captured from the training experiment. I mentioned we uploaded our data to Label Studio. So just so you can see what this data looks like. Here's a sample of some of our training data. And if I click on this, we can see some of the labels. We basically identified 3 classes of defects, what we'll call broken teeth, a dent, and then a scratch, which you'll see in the demo portion of this. And then, as I mentioned, we just simply built a container image, and the output of a chassis experiment looks exactly like this. It's just a container that, again, I can run anywhere. So took this, deployed it in Modsy, added some metadata. Let's go over to our device group again. And this time we created a different device group for this application. You'll notice I actually deployed both versions that we've developed for this particular model. This allows you to do, you know, live bake-offs. You can visually kind of understand how different models are performing, in addition to capturing some monitoring data, you know, as relevant. Now, one thing we didn't talk about in the first demo is how to actually take models from Modsy and deploy them onto a device. And I think this partially covers one of the questions that was asked. We've got our container, you know, sitting in Modsy. All I need to do is select my target device type. In this case, we're going to a Jetson Nano, which has an ARM chip. and I generate commands here. So with 3 lines of code, all I can do is run these lines of code on the device, and that automatically will take care of syncing and downloading the model from Modsy. It requires a one-time internet connection or network connection rather, and then you can run that model disconnected on that device forever. And so with these 3 lines of code, that's all it took. We spun it up and we're running that model on Seth's Jetson Nano. Now, you can automate this further to send this exact type of configuration out to an entire fleet of devices. So, it's not there are ways to automate this and kind of incorporate this into custom scripts. Okay, so let me kick off this Flask app real quick. All right, and if I go to this tab and refresh this, what we can see are some of these predictions in real time, as I mentioned. So you can see that spinning, and what we're looking at, you saw Seth's finger, and you can see kind of these predictions. Now, you could build a much more sophisticated dashboard for the operator to aggregate these results, to see different views across different assembly lines within the factory, something that can help the lives and the efficiency of those factory workers day to day. Something that can automate the detection of defects so that they can then manually inspect them. So just one example, again, that can be scaled out really, across any number of cameras and factories, et cetera. Okay. And we can address some more of those questions in a bit more detail in a couple minutes. But
one of the things we didn't show off in that particular demo is the fact that this provides a bidirectional connection back to kind of your central model hub. We'd really recommend that kind of thinking. Again, creating communication so that your edge device, edge-centric thinking, of course, your edge device can call back to the hub, get the information it needs, get the model, get any configuration data, get information about whether or not to use a GPU if it's available, things like that. But then you can also share information back to that hub, so there's a central view. And so one of the ways that can be used in a scenario like this is returning samples of the live inferences, because that sample data is what data scientists can then use to figure out, hey, how's this model doing? Was there a change in the production process such that the model we built last week is basically finding more false positives or missing errors, and there's a lot more false negatives? Let's retrain a model, and then we'll, again, configure within your central model library, your central hub, that there's a new version of this model. And then each edge device can kind of just be listening. As soon as that model's available, it will stop the old model, download the new model, restart with that new model version. So having that bidirectional communication is it's a godsend for operations, because then you don't have to manually be one-off updating all of these devices with all of these new model changes that you've got to make in a scenario where that performance becomes really, really important. All right, so one last demo we want to share for you. We've showed so far examples where we're running one model on one device, which is great. A lot of great things to be learned from that. But one of the benefits of edge-centric thinking is the fact that as soon as it scales up to more than a handful of devices, it becomes totally unwieldy. There's just not enough hours in the day for an operations team to manage it all. And it's quite difficult to keep these models in good working order and know how they're doing. So we've created an example of what it would look like if you created a computer vision driven parking lot. So rather than using that old-fashioned RFID technology where you give each of your customers a little chip to scan at the gate and the arm comes up and you walk in, let's replace that with a model that just detects license plates. Why might you do this? Well, there's all kinds of interesting things you could do with that. It gives you live data about who your customers are, which garages they're parking in. Gives you the ability to do all of that processing locally. If you're actually running those computer vision models right at each location, it means that the garage can keep working even if the internet goes down. It wouldn't be super fun to tell your customers that they couldn't leave the garage because Cozy Bear did a DDoS attack on AWS East. Not a fun reason to be locked inside of your parking garage. So for a lot of those reasons, you could take advantage of machine learning to completely transform the operations of your family of parking lots. But you have this challenge of how do you get these models out to each one of these garages all over the place? Well, that's what we're going to show off today with this example. So we've got, again, our central model store up in the cloud. that's Modsy, we're going to be sending out the models to 20 different devices, 20 different edge servers. These are relatively small edge servers as well. So these could be provided by, just a simple desktop tower, kind of an industrial desktop tower sitting in the kiosk right in the parking garage. It could even be run on a relatively small edge device with 4 cores and 16 gigs of RAM. And then we're going to be connecting a live data stream to a license plate detection model that's running on each of these devices. And then we'll see an aggregated data view of all of that, all of those feeds from your 20 different garages all in one spot. So I'll go ahead and switch over so that I can share my screen and give you guys a sense of what that's going to look like. And there we go. Okay, can you guys see my screen okay?
Yep, sure can.
All right. Awesome, thanks, Brad. So I'll just show you this license plate detection model that we have. This is an open source model. To be honest, it's not particularly good, but it does perfectly fine for the point of the demonstration. We can see some of the information about the model that's being used. And I'll just show an example of what this model actually produces. So it takes in imagery data. It tries to identify a license plate, draws a bounding box around that license plate, and then attempts to predict and transcribe the text that you find on that license plate. So we're just running this in the central model hub for testing purposes. Just to see a quick example, for this particular car, it found a bounding box with a value of Control Z, and that is actually correct. So that's one snapshot of a stream of video that might be coming in from your from a camera at one location. So I'll jump over to our edge device group for the parking lot management platform. So what we can see here again is we've got a collection here of 20 different devices, all loaded with this license plate detection model. They each independently connect and integrate with the system. And then when they're connected, they're able to tell us information about the physical device. We got 4 cores and 4 gigs of RAM here at this location at 1639 Borough Place. And it has access to this license plate detection model version 0.0.1. So what does that look like in terms of actual processing? Here's an example of sample video feeds processed through this model, generating these bounding boxes. But really the magic here is that we're able to run this across all 20 different locations simultaneously. So this is just a raw output, not formatted, of each of these locations independently processing different inputs, identifying, trying to transcribe those license plates, and then returning them back here to my laptop. And so the idea here is that you can take these results, you can take these inferences and predictions coming from 20 different locations and pipe them into other management tools. So this might go into my customer relationship management tool, and I can figure out which of my customers' vehicles are they using day to day, which locations are most popular. Maybe I want to use this information to help calculate demand-based pricing based on which vehicles show up at which garages at which times of day. It provides the ability to start mining this data that's at the edge using machine learning and then pipelining just the results rather than the raw data itself back to the systems that I use to manage my giant parking lot management company. Now, I do not actually have a parking lot management company, unfortunately, as much as I would love the extra revenue. So we're simulating this across 20 different devices spread across a bunch of different AWS regions, but it performs the same concept where we're independently processing video streams through each of these locations and allowing us to pipeline the results right back here. So that was the last demo we wanted to share. Just as a couple final thoughts here, I'll pop up the presentation one last time, and hopefully this shows up. There we go. So, Brad, myself, Lady Gaga, we would love all of you to join us at the Edge of Glory. And, to do so, we really encourage you to consider an edge-centric architecture anytime you need low latency, high performance, offline and online execution. Or you just have models that have to compute or run compute on more than one computer. If any of those are true for your use case, edge-centric thinking can really, really help. And start small. You don't have to solve all of your challenges all at once with this approach, but prep for scale, prepare, develop a solution and a mechanism and connection approach that will allow you to add more devices, more models, more locations, more use cases as you learn more and grow. So that's everything we had for today. Thank you all so much for joining the webinar. It was absolute blast to be able to share this with you, share some demos, and chat. So at this point, I think we can go actually take a few questions if you'd like, Brad.